Okay. A very good afternoon to everyone, and welcome back to the vertical 2 of DDH 2020 training program. In today's session, we have with us Dr. Madhavi Sastry. Dr. Madhavi has done her PhD in quantum mechanics at University of Hyderabad with Professor Durga Prasad. She did her postdoc in Fritz Haber Center of Molecular Dynamics in Jerusalem, followed by a further stint at University of Fribourg, Switzerland. After returning to India, she worked in academics and industry. Presently, she is working on theoretical and computational chemistry and biology at DE and Shaw and Corporation for Schrodinger, based on New York. She has published papers in reputed journals spanning physics, chemistry, and biology. In today's session, she'll be talking about hydration side thermodynamics for molecular recognition. I now hand over this session to Dr. Madhavi ma'am.
Hello, good morning to everyone. So, Hriday Jyoti, can you hear me?
Yes, ma'am.
Is my voice audible?
It's perfect.
Okay, so great. Good afternoon, everyone, and it's nice speaking to everybody who is attending this session. And I'll be talking about something different in terms of drug discovery. So this is more on in silico methods which are applied to drug discovery. And I think most of you must have heard people talking on various parts of the drug discovery program. So in general, the drug discovery programs start with the screening of large number of molecules and zeroing in down and designing compounds. So nowadays, most of it is done at the initial stage using in silico methods. And then later on, it goes to the, once the suggestions of molecules are given to med chemists, they synthesize, and then the biologists try to do cell assays and find out the biological properties, experimental properties of these compounds and proteins before it goes to trials, whether it's animal models or clinical trials before the FDA approval. So I'll be focusing on a specific topic today of in silico methods, and more specifically to a method which deals with waters in a protein cavity. And waters are there everywhere. So let me start off with the next slide. Okay, sorry. How do I go to the next slide? I think I'm missing the next slide. Okay, so generally what we do is, here you have the protein cavity. The protein is a very big molecule, and in its cavity it can accommodate small molecules, and these small molecules could be drug-like. And there are so many possibilities, several small molecules that can go and sit in the protein cavity. So which is the molecule which could ideally be a putative drug? So there are many factors that contribute to it. And when you consider small molecules in the protein, one is always only talking about the binding affinities. That is equilibrium thermodynamics. But the whole drug discovery process has a lot more other components, but we'll be focusing on this part. Now, there are interactions that the molecule can make with the protein, with waters. But when the ligand gets into the protein pocket, I call it as a ligand, but it could be a possible drug. And when it gets into this huge protein pocket, and it actually evacuates some of this water to the bulk. So it's enters the pocket and throws out some waters. So which waters does it throw out? Why does it throw out? Why do waters actually get into the pocket? And how do they help us in understanding which molecule binds better is what we are going to talk about in today's session. So we will predict the positions of the waters and the thermodynamics of the water molecules. So I generally like this slide. I keep it or most of the times. So if this is a pocket of thrombin, which is an anti-cancer target, which is a protein, and the proteins are, as I said, large molecules, and then this is a pocket of a protein, and there are certain water molecules. The green ones, I call them as happy waters or stable waters. They are stable with respect to the bulk. So as I told you here, pocket from the bulk. And when they're thrown out of the pocket, they go back to the bulk. So the bulk solvent. So these are the, so why do they go into the pockets? So after they go into the pocket, some waters can be more stable with respect to the bulk, and some waters can be more unstable. Which is shown here by the red color molecule, which is a water oxygen. So this is how a map looks like, and I'll show you how it can be used to design compounds. So in the thrombin pocket, you will see molecules here which are very happy or stable and unhappy water. Now this is a possible organic molecule which can be a drug, but probably not, because it has a very high IC50 value. So lesser the IC50 value, the better. Lesser the concentration to inhibit the action of the protein, the better. So let's say this is 10,000 nanomolar is the IC50 of this small molecule. What is this doing? It is actually displacing 3 waters. It's colliding with 3 waters when it goes into the pocket and throws out these 3 waters. Now you do a modification to this molecule, add a halogen here, remove this group. You are avoiding this molecule. So water that is happy would like to stay there. It doesn't want to go out of the pocket. So it's better to avoid those. And now this, when you make a modification to this ligand, this is avoiding this water, which is a happy one, and it is getting closer to the unhappy water. So you see that the IC50 value has gone down. As I said, the lower the IC50 value, the better. It's 9,000 nanomolar. Now you go further and do a little bit more modifications, and then you will see that this particular compound can now totally avoid this happy water, keeping it in place. And so the IC50 value has gone down further. Now you make a modification of an ether linkage. And then you see that this molecule is trying to displace this particular unhappy water. Unhappy water which is unhappy in the pocket would like to get out of the pocket. So this unhappy water is now trying to be hit by the molecule or trying to be thrown out, and the IC50 value goes down still further to 89 nanomolar. And after doing this particular changes to the ligand modifications, you will see that the IC50 has gone down to 3 nanomolar. That's a very good improvement from 10,000 to 3. This is because it's totally avoiding this water, but then it is throwing out this unhappy water. So this is the basis of what the whole methodology will be on, where we will try to identify or calculate using certain theoretical principles the delta G of each of the water molecule with respect to the bulk. So that will give you a quantitative field. Now this is all qualitative, what you see now, pushing out waters, keeping waters, and doing modifications. The next, in the following parts of the talk, I'm going to talk about the quantitative picture also. But before we go to that, so how can these waters in the binding cavity behave? So when a ligand goes and sits into the protein pocket, like a lock and key mechanism, it can just simply displace a water molecule, as we saw just now. And if this water molecule is a high energy water molecule, then that contributes to the binding affinity of the ligand. That means if it can displace a very unhappy and stable water, then that molecule can have better binding affinity to the protein. The better the binding affinity to the protein, the better the chances that it has the desired thermodynamic properties of a drug-like molecule. The other option is replace, where we can, there's a water molecule in the pocket and it can form hydrogen bond interactions with the protein. Now, if the ligand or the drug, I'll use the word ligand throughout and not drug-like or putative drug, but it basically means that if a ligand can replace a water molecule which is forming an interaction with the protein, and then what happens is if the ligand can itself form an interaction with the protein while displacing the water, then you call it replace. I will show you examples for this. Interact is occurs when we decorate a ligand with a group that can interact favorably with waters, which are nearby in the cavity. And then there are regions of the avoid is there are regions of the binding cavity which have a cluster of very stable water molecules. And when we design compounds in the cavity, we shouldn't be bothering to displace that particular cluster, or basically we avoid that part of the binding site. So the individual hydrate, the thermodynamics of the individual hydration sites is what will determine how we are going to design compounds. Now, for example, displacement, you have a compound here, and you know delta G is equal to delta H minus T delta S. Now, these are all again with respect to bulk. Please keep in mind that all the time. Now, if the delta G is positive of a water molecule, that means that water molecule is unhappy or unstable. Now, if delta H is also positive, that means this water molecule is unstable and is not making any favorable interactions with the protein as compared to what it is making with the bulk water. So in that scenario, this water molecule is enthalpically unstable and of course entropically unstable. And so just by adding some simple groups what you say methyl or halides to this, making a small modification, one can displace this water and this water. Both are high energy waters. That is, both are waters with delta G equal to positive. In such a so you can modify the ligand in such a way that you displace these two and gain in the potency of the molecule. So you see this water has a delta G of 6.29 kcal and this water has a delta G of 3.57, and these are calculated values. So displace these two and then the ligand will have a better binding affinity. Replacement. So as I was telling you earlier, these are the waters, and these waters can make interactions with the protein. So if one wants to displace these type of waters, then one could add a polar group, let's say something like an amine, which can form a similar interaction that the water was forming with the protein and displace. That means there is no loss of interactions while displacing a water molecule. So interactions decide here on what type of groups can be added. So that's one way to decide what groups can be added to displace a water molecule. You can see here the delta H is negative here, minus 4.6 kcal. That means these water molecules are forming interactions with the protein. So you make a modification to actually preserve those interactions. Now there is another point where these water molecules are highly conserved, very conserved, and delta G is less than equal to 0. And these waters can form bridging interactions between the ligand and the protein. Okay, so they are displacing or replacing these is very difficult, and one can actually treat these water molecules as more or less conserved, and the delta G of these is 0.73, and so it's purely an entropically driven process. Now avoidance, it's very hard to do anything when you have cluster of water molecules which are highly stable in the protein pocket, because displacing them is actually costing the ligand molecule of energy. So we would like to avoid those regions. Now again, as I said before, what do these terms correspond to? So the values calculated correspond to the average excess enthalpy, entropy, free energy that a water molecule located at the hydration site would possess. So if you say this is where some of the water molecules that you see here get into the pocket, this is the protein, the red one, and then delta G would be that when a ligand gets in, the waters are thrown out of the pocket. So that would contribute to the delta G. So the delta G of each of the water molecule will contribute to the binding of the ligand of the protein. Remember, we are ignoring a few other terms during this binding process, which I'm going to come to later. So a negative delta H value means with delta G, as we know, is delta H minus T delta S. Delta S is always positive because a water coming from bulk and getting into the protein gets restricted. So when it's getting restricted, there is a high entropy cost. So in that situation, entropy is always going to be positive. So the determining factor would be whether how negative or positive is delta H, then delta S, the entropy. A negative delta H makes stronger interactions with the protein and with the surrounding water molecules, whereas the positive delta H makes weaker interactions. The water with positive delta H makes weaker interaction relative to the bulk. Always remember, this is relative to the bulk water. Similarly, every interaction with the protein has a entropic penalty. This is what I was saying. So when the water gets into the pocket, it is restricted now. It doesn't want to get restricted. If it is happy sitting outside in the bulk, then why should it go and arrest itself in the pocket of a protein? So the magnitude of, every interaction with the protein has a entropic penalty. Okay, so it is favorable to displace a water molecule when delta G is greater than 0. It costs energy to displace a molecule with delta G less than 0. So each of the hydration site or water, I may be using the term hydration site more or sometimes water. So any water with delta G less than 0, we prefer to displace that. And this displacement is brought about by the ligand binding to the protein. So as I showed you in the earlier slides, when the ligand gets into the pocket, it displaces these high energy delta G water molecules or hydration sites, as well as some low energy, less than 0 hydration sites. Now, what happens during the calculation? So initially, a molecular dynamic simulation is what is done, and the simulation production run is about 2 nanoseconds. And we use TIP4P solvation model. And then once during the dynamics, we take the frames of each of throughout the dynamics of the protein system, and then we cluster the water molecules spatially orientally. Then once you cluster the molecules, then you get the water density, the number of molecules per unit volume, and then get a distribution of the water density. And so we get wherever we get spatially distinct peak in the distribution, we use that as a position of a hydration site. The clustering algorithm terminates when there are no more distinct, spatially distinct peaks with a density greater than 2 times the bulk density of the water. So after this clustering is done, the next step would be calculating the thermodynamic properties of each of the water that showed a peak in the spatially clustered water molecule distribution. So in that, what we would do is the next step would be to calculate the thermodynamic properties. But before that, I would like to say that when we are doing the calculation, we restrain the protein. So we do not allow the protein to move much except a few terminal dihedrals or some hydroxyls, which are allowed to move. And this is because when you restrain a system, you're making sure that the protein is stuck to a particular arrangement. Okay. And you don't want the results to be polluted by the rearrangements of the protein. And especially when we calculate an APO water map, APO is when the ligand, we consider that the ligand is not in the pocket. But we use the crystal structure of the protein ligand complex. And when the ligand is removed and then calculate, the water hydration sites are calculated, the problem could be that if the protein is not sufficiently rigid, then it can collapse. So, which is one reason why we restrain the protein in the water map simulations. So, however, we used we generate water map results on only one complex to score some non-native ligands. Now, but we all know that proteins are fairly flexible, and in the solvent medium, they adopt several conformations. So how transferable are these results? That is, you use a specific conformation and taking decisions on that conformation. So how transferable are these results across different ligands? So from our experience of studying various systems, we realize that whenever you have ligands which are very similar or congeneric set of organic compounds, what the results generator are very well in sync with each other, because when the ligands are similar, we assume that the protein structure doesn't change much. And in that scenario, the idea can be transferable across different compounds. And moreover, in mobile regions of protein, where reorganization is trivial, then water map can be less transferable across ideas. So we have to know where exactly each methodology can be adopted and not use these methodologies blindly on any system. So, and there are several methodologies, and we need to make sure which one works best and what is it tailored to. Now, why do we see sites with delta G0? So why is it that water molecules which are very highly stable in the bulk solvent go into the pocket where their delta G is greater than 0, that is, they are unstable? Why don't these molecules spontaneously leave the pocket? Why do they even sit there? So one thing that we ignored here is, while doing the reason why we see unstable water molecules or hydration sites in the protein pocket, is that we are looking at condensed phase. So if you read this statement, estimates suggest that penalty for a single water size vacuum in a cavity would be about 6 to 8 kcal per mole. So having a cavity or a vacuum in a protein site can be more energetically unfavorable than having a water molecule with delta G greater than 0. And this 6 to 8 kcal bias holding the water is what is actually holding the high energy water molecules in place. Okay, and these are when the environment becomes more unfavorable, then what you get is de-wetted regions or evacuated regions of the protein cavity. And these evacuated de-wetted regions are actually very interesting regions which can be later on exploited to design ligands. So again, we'll come to that later, but just keep this in mind. Now, I was telling you that there are many terms that miss in this water map calculation, scoring and calculations. So the whole thermodynamic decomposition of ligand protein binding is this given here. So first you have a solvated ligand and you have a solvated protein. Protein sans the ligand, and this solvated ligand gets into a bioactive conformation. That means it adjusts its shape in a way that it can get into the protein pocket. And similarly, the protein adjusts itself in a ligand-induced conformation. And then the ligand gets desolvated. That means the water around the ligand it's desolvated. And similarly, the protein binding set gets desolvated, which is ligand-induced. And then both of them form a protein ligand water complex. And the sum of all this, we know delta G is a state variable. So sum of all this would give to the delta G of binding of a ligand to a protein. And by using water map, we are just calculating this term in the entire thermodynamic cycle. So this term is solvated protein in ligand induced conformation. And these waters can give you that term of the binding energy in the entire summation of the delta G bind. So only those systems where these other parts of this thermodynamic cycle are constant is where this methodology works. So we have to keep that in mind. So the methodology is, again, as I said, 2 nanosecond MD simulation is run, waters are spatially clustered, entropy and enthalpy of each water molecule is calculated. How do you calculate that? So entropy, enthalpy comes directly from the non-bonded interactions, ligand and the protein or any other parts of the system. Whereas, and that is from the force field. If any of you can understand computational and theoretical methods, force field can give you a good estimate of the internal energy, which actually calculates the non-bonded interactions. And then the entropy is obtained from a local expansion of spatial and orientational correlation functions. So this is how it looks like. The entropy, the delta S values are calculated using inhomogeneous solvation theory. So this is basically an intelligently modified series of integrals where you will see distribution functions and pair correlation functions. And each of this integral measures the entropy of the position and orientation of the water molecules of each of the water molecule or each of the hydration site in the protein. So it's a series of integrals. It looks a bit lot, but it's not really that bad. Now, so this is the inhomogeneous solvation theory, and I should say that it looks very messy. And this was by Lazaridis group, where you see that you have a distribution functions. This is the distribution function of solute and the water solute being the ligand protein system. And this orientational distribution functions are assumed to be invariant in each subvolume of the hydration size. So when you're calculating this pair correlation function, you assume that the water is distributed uniformly around it, and then use a representation of Euler angle or quaternion angles, because it makes it easy to do the integrals and because it becomes more periodic boundary conditions. So this is what it looks like, but it's not that difficult. Again, I'll get to that. Now, so as I said, so using the inhomogeneous solvation theory, the entropy term is calculated, and using delta H, the enthalpy term is calculated. Now, once enthalpy and entropy is calculated, you can calculate delta G, which is delta H minus T delta S. So then the way the ligand is scored based on how it displaces the water. That's what is done. You do a scoring of the ligand, which actually gives you the binding, which actually should correlate with the binding with the protein or the binding affinity. So, but with the disclaimer that certain situations or certain terms in the thermodynamic cycle should be constant. Now here, O is the overlap between atom A with the hydration site S and delta Gs of that hydration site. If you calculate the overlap times the delta Gs and sum for all hydration sites and atoms, then what you get is a scoring function of that particular ligand. So, so this is how it looks, and this is the final scoring, which is also published in this paper in 2008. So delta G bind is given in terms of the distance of the hydration site from the ligand and a Heaviside step function, which is equal to 0 or 1. If it is equal to the cutoff energy or internal energy, then it's 0, and anything about the cutoff energy of the hydration site is equal to 1. And then similarly, the entropy terms, and which use a Heaviside step function to make sure that we are within the 0-1 limits. And this is how it looks. I mean, I should say in reality, this offensive mathematics is doing something that is very obvious. That is, it's just quantifying the randomness of the water molecules that occupy each hydration site. So how random they are, how uniform they are. Anything that is deviating from the uniformity of the solvent distribution is your delta S. That's your that gives you the estimate of your delta S. So that's basically how the entropy factor is calculated. Now, as I said earlier, there are so many ways to do computational theoretical methods to design drugs. So, as I told you again, there are many terms that are ignored in the overall binding process. So this method would be valid only if the ligands are highly similar, so that they have a similar conformational penalty. That means the conformational changes will be similar to all the ligands. In that situation, it can work. And then the various ligands interact with protein, and so it could work only when these ligands, all the ligands that we are looking at, form similar interactions with the protein. So it is, in that scenario, it's a very good method for doing lead optimization. And I will also talk about a few other things which, because this method is very sensitive to changes in the protein, it can be, that sensitivity can be used for identifying selective molecules. So this may seem limiting, that only when ligands are similar that this could work, but many a time when we do, when med chemists design compounds, just adding a simple methyl group at some position of the organic molecule or a putative drug gives a huge gain in potency. Why is it happening? Because this methyl group is not forming any added interactions. So just by adding it, why is it happening? So one possible very good reason is that this is displacing some high energy water. So it's not really interacting. So these magic methyl effects can be delineated through this method. And one can decide where all can we add methyl groups to get the sudden gain in potency of the ligands, or the binding of the ligands to the protein. Now, a lot of research we have been doing over the years, and this is one research where just to identify what are the magnitudes of delta H, delta S, delta G that can take for proteins and the waters and hydration sites in the proteins. What is the range of the magnitudes? So a data set was taken and 32,000 hydration sites across 27 different proteins were analyzed. And when we looked at the delta H values, we see that, and look at the distribution of delta H, we see that there is a peak at minus 4 kcal per mole and somewhat a very light peak at minus 2 kcal per mole. And then all the 0 kcal per mole for uncharged groups. So this minus 4 kcal per mole are those delta H values which form interactions with the acidic groups. Minus 2 is for basic groups, that's what we notice, like amine and stuff. And 0 is for interactions with non-uncharged groups. So this is one distribution just to understand what ranges the values can take. So delta S, we know, will have to be positive because now the water molecules are arrested in the protein, so they have to be positive. And I should say at this point that when the distribution was done, we saw that it tapers down at 6 kcal per mole. And that is the entropy loss of transferring a water molecule from gas phase to ice crystal. So since all of these are X-ray structures which are analyzed, and the 6.3 kcal is the entropy loss, this exactly matches with what we see when we look at the distribution over several proteins and hydration sites. And then there is the delta G values. And then we see some of the hydration sites which can even go as as unstable as 8 kcal per mole. And again, this is in line with concerning vacuum formation. So when there is a vacuum formed in a protein cavity, that's a highly unstable situation, and that can be as unstable as 8 kcal per mole. So that delta S that is you see in this distribution is tapering down to 8 kcal per mole, which fairly is in sync with what we notice in experiments. Now, what is the solvent effect of solvent accessible surface area? So we know that if a water is exposed and take a hydration site is completely exposed and say that it has about 1.4 angstrom radius, then the SASA, the surface area, it would be around 72 angstrom square. But such hydrations are fully solvent exposed and should have a delta G of 0 because That is what we take as a reference. But we see all the hydration sites, the water molecules which have greater than 2 kcal per mole, have a very small solvent accessible surface area. That is, they are very much buried in the protein cavity. But it doesn't mean that all the buried water molecules in the protein cavity have delta G greater than 2 kcal per mole. There are also water molecules buried in the protein cavity with delta G less than that. So we need to be very much aware that just by looking at the structure alone, we cannot come to conclusions, which is the reason we need a quantitative estimate and do all these calculations that you saw earlier, or in a way, offensive mathematics. Now, this is one example of how you can use it for real life purpose, real life molecule design. So in this paper by Kung et al., we have a 22 micromolar compound. And then from this 22 micromolar, they designed a compound of 15 nanomolar. So this is a high increase in potency, micromolar to nanomolar. We'll show you how one can use water map to do this. So this is compound 3, and you see this has a phenyl ring and this ring here, heterocyclic. If you go further into the phenyl ring here, one can add a halogen and a halogen because there are 2 unstable hydration sites that one can see here. One has 3.6 kcal per mole delta G, one is 6.3 kcal. And if you add a halogen here, that can displace this water. Add a halogen here on the phenyl ring, it can displace this red color water, this highly unstable water molecule. So a compound 6 is designed, which now has 0.35 micromolar. 22 to 0.35 is again a decent gain in potency, just by adding halogens, because we know there are water molecules here and we can use these halogen substitutions to displace them. Now, if you look at this, the same scaffold here, and you see certain R groups, what are these R groups? Look at R1 and R2 positions. Wherever R1 and R2 are occupied by some groups other than hydrogen, you see a gain in potency. Look at compound 3, where R1 and R2 are hydrogens, or even R2 is a hydrogen in compound 4. You see they are like 22 and 7.9 micromolar. But you occupy R2 with some group and the potency has increased. That's because at R2 there is a highly unstable hydration site. Similarly at R1. So we are making, and so if you look at the structure activity relationship here, SAR, you will see that the water displacement seems to perfectly explain why one should use certain substitutions at certain positions on the ligand molecule. Now let's go beyond compound 6 and 7. And if you look here, there are certain water molecules. There's a water molecules here, which is about 0.33 kcal per mole. There is a water molecule here, which is about delta G 4.7 and 4.42 here. How about displacing these 3? If we can, then again one can gain a huge potency. Now, how do you do that? So look at this region here. How about using a scaffold hopping? Put another ring here and push these substituents further to displace all the 3 at one time. So that's what was done here. So if you, a pyrimidine ring which was there in the previous molecule, it's changed to a pyrrolopyrimidine. And now it is able to displace this water, and behind there is another water. So there's a huge gain in potency for this compound 17.015 micromolar. So by using the water hydration site thermodynamics, one can design ligands with certain clauses to gain molecules with higher potency. Now I'm going to talk about another example system where this is a work that I did with the Harvard group of Professor George Whitesides, and we were studying human carbonic anhydrase. This is a collaboration, and this carbonic anhydrase catalyzes several reversible hydration of carbon dioxide. And defects here can cause osteoporosis and renal tubular acidosis. So let us understand role of water in this particular protein cavity. We notice that this is a very rigid pocket for this protein, and waters can really play a major role. And the experiments were done in the lab of George Whitesides and collaborators, and we did all the theoretical and computational analysis. And so what we did is we took human and carbonic anhydrase and looked at the water rearrangements due to the residue mutations. So we had two ligands, that's here, TA and BTA, sulfonamide moieties, containing sulfonamide moieties. And we looked at the binding of these to the protein in the presence of certain mutants. So what's really happening? That is, can we do a mutation in such a way that we can design ligands in a way that leads to a favorable arrangement of the water networks in the protein cavity? So this was published in Anguante Chemie in 2017. And and before we do any calculations, we always make sure that the protein structure is properly refined in terms of the hydroxyl groups, the orientations, and in terms of the tautomeric states of histidine and other particular residues. A lot of analysis of the structure and cleaning of the structure is done. And how do we do it? That whole methodology is described in this paper of which I worked on with some of our colleagues. And this paper has presently has 1764 citations so far. It was published in 2013. And so we have used that for cleaning up the proteins before doing further calculations. Now, the group there did all the isothermal calorimetry experiments, and from the isothermal calorimetry, before we even try to predict anything using our methodologies, we need to first validate every time when that our methodology works for the system. So the group had the ITC data wherein they had delta H and T delta S values obtained from isothermal calorimetry, and we did the calculations. And when we did the calculations, if you look at this graph, the solid lines are experimental values and the solid spheres, and the other spheres, open spheres, are theoretical values, and they match very well. And once we are sure that this is validated and the results are matching with each other, we can go further and do predictions. Now, there is a leucine 198A, and we did some sort of a sequence analysis before coming to this, wherein we predicted which could be certain mutations which can help in trying to design new ligands and understand the rearrangement of water networks. So L198, the leucine of is mutated to alanine. And so obviously now the cleft enlarges, the pocket enlarges, and the water network gets expanded. This is the ligand, and this is the leucine in the wild type, and the mutant leucine, it's like this. And you see the cleft enlarged, and you have more water molecules here compared to here. In the presence of the ligand, this is the leucine, which is mutated to alanine. And in the presence of the ligand, we see that the waters undergo enthalpically unfavorable rearrangement. So when the ligand is binding and leucine is mutated to alanine, waters rearrange, but they have an enthalpically unfavorable terms, due to which delta G is positive. So the binding is entropy driven. So why should the ligand bind if these waters are becoming enthalpically unfavorable in terms of interactions? Why should this bind? That means this is binding because of the entropy factor. So this binding is entropy driven. Remember, delta G is delta H minus 2 delta S. So we are based on that. If delta H is not contributing to the binding, then delta S is contributing to the binding. We did a double mutant, and then also besides mutating leucine to alanine, we also mutated phenylalanine to tyrosine. And here it is. So you have the wild type, and then we mutated the residues here. And this is ligand, one of the smaller ligands is at the bigger ligands, the BTA. When TA binds, obviously being a small ligand, the water network doesn't change too much. But when BTA binds, this extra benzyl ring, the phenyl ring that's here, again makes an enthalpically unfavorable rearrangement. So the arrow here, if you see, highlights the enthalpically unstable water hydration site. And again here, binding is entropically driven. So we have to look for residue mutations which give a rearrangement which can help in the rearrangement of the hydration sites, which can help in the ligand binding. So what are the different strategies that we learned from this is enthalpically favorable. If we have enthalpically favorable rearrangements, that's still better. If we don't, if we have entropically favorable, then that means enthalpically, let's say they're unfavorable, then perhaps the binding pockets of give rise to stronger protein ligand associations. Now, mutations can enhance the enthalpic benefit by rearranging the water molecules. And while one might expect free energy and enthalpy to be correlated, the nature of this correlation is primarily to influence the mutations on local water networks. So mutations that decrease hydrophilicity of amino acids near the nonpolar surfaces are likely to increase its affinity for ligands. So we are just trying to analyze and reason out the structure by doing a certain mutations of the residues to see which could ideally help in the ligand binding. Again, there was another project that we did, collaboration with the Harvard group, where we studied what is the effect of ions in the protein cavity, especially HCA2, human carbonic anhydrase. And then we studied cosmotropes and chaeotropes. And cosmotropes are ions which tend to stabilize the folded proteins. They're strongly hydrated and small, like Na plus and things like that. Chaeotropes tend to promote denaturation of a protein. So protein becomes denatured and gets more soluble in solution. So earlier studies suggest the effect of ions is limited to first hydration cells. So the ions don't have too much effect beyond a certain hydration cell. That means the entire protein pocket may not be affected by these type of ions is what was studied. And here we got a different result. So we did MD simulations, we did these anions upon associating with zinc trigger rearrangements of water is what we noticed. And I will talk more about this in the next slide. And we see that, for example, thiocyanate triggers rearrangements of water that extend up to 8 angstroms from the surface. So it's not just the first hydration cell. This is again a validation of our experimental results. And this is to understand till where is the hydration cell going to be affected by the presence of ions. So till 8 angstroms, so it goes beyond the first hydration cell. For example, here I show that you have these 2 hydration sites in the protein pocket, and a binding of iodide displaces these 2. And that actually helps in creating a rearrangement of the water molecules, which can help in the ligand binding in such a way. So these are the 2 examples, and this was published in JAC. I mean, there's a slight format problem when I transferred it here. So yeah, sorry to this machine. Okay, so this was published in JACS, this work. And after this, there's a few other examples like druggability and water. So if your binding site has large number of unstable water molecules, then that could be a very good druggable site. So the number of hydration sites gives the volume. It's a measure of the volume of part of the binding cavity could be well occupied by the ligand, and the energy of the hydration sites give you an idea of how druggable is the pocket. Now let's look at Gleevec, which is of the ABL. And Gleevec sits like this in the protein, and you see how all these red colored water molecules, the way they are, I mean, they form a similar pattern like Gleevec, showing you that It's a highly druggable product, highly druggable pocket of ABL. So these actually provide a useful indication of the shape of an ideal molecule in this case. And this is reinforced by water map. Now you look at the PTP1B, that's another drug target, sorry, and you see a very stable water molecules, large number of stable water molecules in the pocket. So hydrophobic atoms here are actually detrimental to the binding. Only powerfully, so in such a situations, only if your ligand is highly polar, it can bind, but then it has other problems. Hydrophilicity is a big problem because one has to, the ligands have to cross the lipophilic barrier. And so that would be a problem. And I think there are a scattering of hydrophobic regions away from the main binding set. And even if you get some ligands which can sit here, they would be largely inefficient. Now, selectivity. So the problem that we face most of the time in drug discovery design is that you would like your compound to bind to certain protein but not others. And this becomes more difficult when the other proteins are very similar to the protein of interest that you are targeting. So when they're very similar, then the organic molecule that binds to your protein of interest can go and bind to the other proteins also. In such situations, what you get are side effects. So many a time we want to avoid such situations. So to avoid such situations, you need a methodology which is very, very sensitive to subtle changes in the structure of the protein cavity. And so in that scenario, a small difference, we see that whenever we do a water map calculation, we see that a very small difference on structural change can rearrange the water molecule significantly. And this property of the method can be used to identify selective compounds for a particular disease. Now, the other thing is cavity maps. So there are two reasons to not see any hydration sites. So so sometimes in your water map calculation, you don't see, there are certain regions where you don't see any hydration sites or any waters predicted. There can be two reasons. One is that the water here behaves like bulk water. In such a situation, you won't see that, or there is no water in that region. And as I told you earlier during the presentation, I said that can be a very highly interesting region because these regions are very unfavorable. So trying to put a ligand in the part of the ligand or make a substitution on the ligand such a way that it can occupy these regions can be very helpful in gaining the potency. Now, what is a cavity map? How do we detect it? So we insert a test particle in the cavity. We attempt to add 1 angstrom test particles. And if the region contains protein, protein ligand water, you cannot insert a test particle. If the region is evacuated, that means there is nothing there, the test particles can be added easily. So we look for those, use a test particle insertion process to identify maps which gives you the probability of the insertion. Higher the probability that you can insert a probe, the more evacuated the region. So why do I say probability? Because we are doing this calculation not on one structure, but through a whole molecular dynamics simulation. So depending on how many of the frames the test particle goes and sits at a particular site, you can get a probability of the region being evacuated or non-evacuated. So I think I have touched base as much as possible, assuming there are many master students as the audience here. And the summary is that we have touched based on a lot of things like predicting and calculating the hydration site thermodynamics, significance of what these delta H, delta G, their signs, etc., imply in terms of protein ligand interactions or no interactions. So trying to understand the thermodynamic properties. I then explained the calculation methodology where I talked about how to calculate the entropy using inhomogeneous solvation theory using pair correlation functions. And then I talked about scoring ligands and talked about some examples for lead optimization in terms of either modifying the ligand or modifying the residues, mutating residues, or using Hofmeister ions and several other things, and discussed a few other example applications for selectivity and druggability, etc. So this is basically the summary of the whole talk. And I should say I thank all the Drug Discovery Hackathon organizers, CSAR NEAST, my colleagues at Schrödinger, colleagues at DESIS, collaborators, investors are Bill Gates and David Shaw, and collaborators for me, for my work was from Harvard. And I thank Lijo, Jyoti Nagamani, and yeah, of course, Himakshi and Jyoti and everybody from here, from NEAST, to have been helping me with this presentation, setting up the presentation for today's talk. And I also thank Dr. Sastry for introducing me to this field, being a pure quantum mechanics person and now trying to apply to drug discovery and related applications. And I thank everybody who has been very helpful in trying to set up the systems and understand my work today. So thank you very much.
Thank you, ma'am. Thank you so much for this.
Thank you, Rida Jyoti. You too.
Thank you for this wonderful and informative session for this vertical. So I will now request Himakshi to take some of the questions from the people who attended. So I now hand over to Himakshi.
Thank you, ma'am. On behalf of DDH team and Director CSR NEAST, Dr. G. Narahari Sastry, we thank you for accepting our invitation and delivering a lecture, a very informative lecture in DDH training program. Ma'am, we received few questions. With your permission, we would like to take the questions, ma'am.
Yeah, let's go ahead, Himakshi.
Thank you, ma'am. So, ma'am, first question is, if the protein is homology modeled, will the water map is applicable?
It depends on, okay, so if you are doing a homology model, then I would suggest, first of all, it will depend on what's your template and what's the similarity between the template and your model, sequence similarity. If it's a highly homologous, and then it should work. And another thing that one could do is one can run water map on a few structures of the homology model where the loops can be different. And if the structure is more rigid, then the chances that it would be more reasonable to apply water map would be very high. But definitely yes, but if one is looking at a very low homology structure, then I would rather suggest you can still apply water map, there is no problem. But the results, I would be very careful to use it for drug discovery purpose. The results can be used for something else, but not for drug discovery in such a situation. Yeah.
Thank you, ma'am. So next question is, how do we practically identify whether water molecules are thermodynamically stable or unstable?
Practically, in the sense, algorithmically you can. That's what I showed today, where we calculated the delta S and delta H. Delta H comes from the force field. So quantitatively you can calculate. And that gives you the thermodynamically, so the summation of the two terms gives you the delta G, and the sign of the delta G tells you if it's negative, it's more stable relative to the bulk, and positive, it's less stable related to the bulk. But that can be done numerically, but just by visualization, you cannot. Many a times one sees the bridged water molecules and it is assumed that they are very stable, but there's a very good chance that they're unstable because there is a huge entropy cost. You are restricting the water molecule through interactions in a certain region, in a certain conformation, so it loses entropy. There's a high entropy cost. So although visually it may seem that it's a stable water, it may not be stable. So there's an entropy factor that needs to be considered.
Thank you, ma'am. So next question we have, what is the importance or impact of solvent accessible surface area in a protein?
Yeah, so what is this importance of solvent accessible surface area? So you mean to say the entire protein, or is it okay? So for a cavity, for a protein cavity, it's always good to have some sort of a structure to the cavity. The cavity is highly solvent exposed, then its druggability will be definitely lesser because the bulk water can easily seep into it. And if the bulk, so you have more of bulk water there. But a pocket which is more closed but has access to the solvent, so that the ligand can come in through a certain channel, would be a more useful pocket to target. But the solvent accessible surface area for ligand design, one can consider if you are designing ligands in the pocket, then if you have polar substituents on the ligand and these are solvent accessible, they are towards the pocket entrance, then that's a highly favorable aspect for the binding that contributes to the binding. Whereas if you have a hydrophobic, which is exposed group, hydrophobic groups are preferred to sit in the pockets. So yeah, so the solvent accessible surface area can play a lot of role in terms of the type of cavity, in terms of the type of ligand. And yes, and anything specific I can answer further on that.
Okay, ma'am. Thank you, ma'am. And another question is, what is lead identification and lead optimization?
Okay, so there are two things to design several now you have, let's say you have COVID. Now nobody knows what are the drugs and there are so many proteins that one can target. By the way, we are also using WaterMap for this. We have some projects going on with pharma companies internationally. But let's say COVID or anything. How do you start designing compounds? There are millions of possibilities of having organic molecules. And out of those millions, many of them can go and sit in the pocket. Now, how do you find out which? So you use methods to identify which type of a molecule sits there. And that is a process of lead identification, identifying the molecule. Once you identify the molecule, that may not give you a good potent molecule because this is one of the many, and this is just a very rough and crude way of identifying. Then you do an optimization of the ligand in a way that the binding potency increases. So you slightly modify either using water thermodynamics or using protein ligand interactions, so anything like that, and start modifying the ligand to fine tune your ligand to get higher potency. And that actually is more in line with lead optimization. That's a very iterative procedure because one goes to the experimental labs, synthesize and test, and if it works or it gets better, they get back to us. And then we do more modifications or we do different changes and then again send them something. It goes in a very highly iterative and fast way, actually.
Thank you, ma'am. Next question is it necessary to put restraint in protein and ligand?
It depends on what type of calculation or system that you're looking at, and what are the quantities that you're looking at. In water map, yes, it is necessary to restrain, which we restrain, but we could also not restrain, keep the protein flexible, or use water map on different conformations of the protein, and in an implicit way incorporate flexibility. One can do that, but in the example, but what I showed you in my slide is we basically take a hollow structure, that means the protein with the ligand, remove the ligand, and then run water map on that. The ligand is only used to identify the pocket. So once you remove the ligand, the protein can collapse. So to avoid that, we restrain here.
Okay, ma'am.
But it's a very general question. Is it necessary to restrain? Not always. It depends on the type of problem that you are dealing with.
Thank you, ma'am. That was the last question. Thank you so much, ma'am, for your nice explanation. Now I would like to hand over the session for concluding remark to Dr. Mahanta. Please, sir.
Thank you, Himakshi. And on behalf of the DDH team and the chairman, Dr. G.N. Sastry, sir, I'd like to thank ma'am once again for taking this session and making it really very informative. So with this, we come and end to this vertical 2 of DDH 2020 training session. And I would like to announce that today we're not holding vertical 3 session because of some circumstances due to the COVID cases in Jorhat. So with this, we come to an end of today's DDH 2020 training program. Thank you, ma'am. Thank you, everyone who attended this program.
Thank you, all of you. Yeah, thank you.